please read the book. There's some really good stuff in here. I'm going to do things just a little bit different than what they do in here, but pretty similar. So let's do it. And I need a new page. Find the right file. All right, there we go. So differentials is the main idea, and we're going to use differentials to estimate errors. So where this all comes from is tangent line approximations. And the idea that the founders of calculus had was this limit at infinity. Oh, do I have to, sorry, hang on a sec. Zoom. All right, so tangent line approximations. Let's take a look at the function f of x equals the square root of x at x equals 4. So we've done lots of tangent lines before, just quick review, and then we're going to test this tangent line out. F prime of x, remember, is our slope function, rate of change function. And so that is 1 over twice the square root of x. I'm hoping that's a derivative you have memorized at this point. To find the tangent line, the point slope form is enormously helpful. Y minus f of a equals f prime of a times x minus a. So I've used this version a lot in Desmos, where I can make kind of a quick tangent line or an interactive tangent line. So point slope form and function notation. For this particular problem, we get, let's see, if we plug in 4, we get 2. So y minus 2 is equal to 1 over 2 times the square root of 4 times x minus 4. And if we clean that up, what do we get? Let's see, square root of 4 is 2. 2 times 2 is 4. So we're going to get a 1/4 times x. 1/4 times -4 would be -1. We're going to add that 2 over to the right. So then we have now y equals 1/4 x plus 1 is the tangent line. So quick check of that in a graph. F of x equals the square root of x, then at the point 4, 2, I think the tangent line is y equals 1/4 x plus 1. All right, so that looks pretty good. I got that tangent line approximation. And when we zoom in on that tangent line approximation, what we see is that as long as we're not too far away from, say, 4 here, like over here at 3 or 5, the tangent line is still pretty darn close to the function. And I can exploit that. And so here's how I'm going to exploit that. What I'm going to do is I'm going to use this tangent line approximation to estimate the square root of 4.1. So here's a question. How do you find a square root without a calculator? I don't know. How do you do that? There are techniques. There weren't calculators in schools when I was in like middle school when we were doing square root type stuff for the first time. And so one of two things happened. We had to look it up in a book. Was one way it happened, or there was a technique for doing square roots, or people used to use things like slide rules. I never got trained to use a slide rule. I just missed that stage of life. But here I can use the tangent line to approximate it. So I'm just saying, hey, let x equal that. And at 4, the square root of x is approximately equal to this 1/4 x plus 1 is my claim. As long as we're not too far away from x equals 4, and 4.1 is not too far away. So then I think this answer is approximately 1/4 of 4.1 plus 1. And if we clean that up a little bit, what do we get? We get 4.1 over 4 plus 1. Let's call that 4 over 4. So then this would be 8.1 over 4. And 8 divided by 4 is 2. 1 divided by 4 is 0.25. So 1/10 divided by 4 would be 0.025. So I think the square root of 4.1 is about 2.025 is my claim there. So let's take a look at that, double check. Square root of 4.1, sorry. 2.0248, so not bad. I got it rounded to the nearest thousandth with just a simple linear approximation with a straight line. So pretty cool. So we can use these tangent lines to make approximations. Now there's a little error in the approximation there, right? So I was off by just a little bit, and we'll talk about how far off I am on these in just a minute, but I wanna relate this to the same idea, but in a slightly different way. So we know that the derivative of a function, f prime of x, which we often call dy dx, comes from, bottom line, right? We have all these shortcut rules, but the reality is that is a limit. It's the limit as, let's say h goes to 0 of f of x plus h minus f of x all over h. Now, if h is close to 0, a small number, then f prime of x is approximately equal to, forget about the limit, it's just approximately equal to this fraction. So f of x plus h minus f of x over h. And h here is just that being close to 0. It's just a small change in x. Okay. Often we call that small change in x delta x. Now, the founders of calculus realized this approaching 0 is problematic because we can't actually get to 0 in most cases because that leads to this 0 over 0 indeterminacy. And so they said, well, really, it's just this infinitesimally small value, kind of like an atom or a subatomic particle, maybe a quark, I don't know. And so they treated dy as a separate value than dx. And so as h goes to 0, h and delta x, by the way, are the same thing. So delta x and h are used interchangeably. That's a number like 0.01, 0.001. But now imagine a number so small we have a hard time writing down its decimal, and the best we can do is just call it delta x. So if we think about that delta x, which is h, going to 0, that morphs into this subatomic particle we're going to call dx here. And this numerator here is my change in y. So f of x plus h minus f of x, that's a change in y. H is a change in x. So what we get is our change in y is approximately equal to the derivative times that small change in x. And oftentimes we will use that with a d instead. Now the d means the limit happened. We tried to get to 0. The delta means it didn't. So the delta means it's a small number like 0.00001. So dy is equal to f prime of x times dx. And remember we talked about the differential form of derivatives before, and that was super helpful in some calculus problems. So I have this slightly other approach right here that I can take. And so now I just want to rethink about this in terms of the function I had a minute ago, which was f of x equals the square root of x. If f of x equals the square root of x, we know that f prime of x is equal to 1 over 2 times the square root of x. And now I'm claiming that a change in y is approximately equal to that derivative, 1 over twice the square root of x, times whatever change in x I pick. A moment ago, I started at x equals 4, and then I looked at x equals 4.1. So that means my change in x here, my delta x, was equal to 0.1 when x was 4. So putting that over here, I can find the change in y, which should be approximately 1 over twice the square root of 4 times that change in x, 0.1, which gives me 1/4 times 0.1, which was that 0.025 I calculated earlier. So that's the change in y. So that's the idea of applying differentials. Now, I was a little off in my calculation there. So if we compare how far off I was, so the actual answer was that square root of 4.1. I predicted the answer to be 4.025. And so, let's see, oh no, 2.025, sorry. And so I was off by just a little tiny bit there. Now it's negative. So that's the actual amount I was off. So I'm going to give that a name. Let's call this E for error. Oh no, they use E for something else. Capital E for error. Yeah, there we go. So that's the amount I was off. I can also look at the percent change. What's the percentage I was off? So that would be just to take the actual amount off and divide by the answer, which was the square root of 4.1. And it's giving me the answer as a negative, but you can see my percent error is wicked small. My actual error is also wicked small. Now, as long as I stay close, I'm okay. The farther out I get, right, the actual error and the percent error both grow together. And so that's what this section is looking at, is using these linear approximations to these complicated calculations. So I'm just going to set up one problem, and then we're not going to actually do it. But I was hoping to get to this. This comes into reality. Anytime we measure stuff and do a calculation, there's a problem. So suppose we are building ball bearings that are used in different machinery, right? So I have this sphere. Note, volume of a sphere is 4/3 pi r cubed. Now we have a machine that makes these things, and no machine is perfect. So when a machine makes this, it's making them based on a radius, right? It's trying to measure the radius when it makes the ball bearing. And you know, suppose we're trying to make a 5 centimeter, or no, let's go smaller, 5 millimeter ball bearing. The bottom line is every ball bearing going to have a radius of exactly 5 millimeters? The answer is no. There's going to be some margin of error in the radius. And let's say our margin of error is a 1/10 of a millimeter. So let's say our delta R, our error, is 0.1 millimeters. The question is, how does that error translate into the volume? What is the associated error in volume? And we can use calculus to estimate these. And so that's what I'm going to show how to find next. How do we find delta V? We're going to approximate it with what we call dV. So we'll get to that in the next class. So thanks for playing today. Sorry we ran out of time for fun with math. We will do more tomorrow.